What's up guys, it's Simon Fiaz and today's video is on aromatic chemistry question paper. I'm going to go through it all. Obviously I've gone through, I'd say, quite a bit of multiple choice questions, and so really now I'm probably going to go through the PMT question papers. The past paper questions like the AS level past papers and all the A level past papers, I don't think I I don't think I'm gonna have enough time for all of that. I'm just gonna do the PMT question papers for each chemistry topic instead, and then I'm just go through the past papers by myself. Since my mocks are start February the 5th, so I definitely won't have a lot of time. Definitely don't have a lot of time. Anyway, question one: Paracetamol's medicine. Yet name the mechanism of reaction. Step one. So I'm going from this and I'm adding an NO2 group. So it's clearly going to be electrophilic substitution. It's just how well you know your mechanisms. So don't complain, oh, I don't get this part of the question if you don't know your mechanisms. Electrophilic substitution. Part B, complete the equation for the reaction in step 2. So I'm going from this to OHNH2, so it's going to be catalytic hydrogenation. So I'm going to need to add hydrogen and I'm going to form water. Now I just need to balance it. Well, I'll get 1, 2, 3, 1, 2, 3, 4, 5. So 5. So if I put a 2 here, that'll give me, okay, so I'll put a 3 here, that'll give me 9. 6, 7 hydrogen, sorry. And if I put 3 there, give me 7. Put 2 here, 4, 5, 6, 7. Okay. In theory, either ethanol chloride, ethanol hydrogen could be used in step 3. Complete the mechanism. Okay. Again, another nice mechanism question. So I got CH3C. Oxygen is going to be here with the lone pair of electrons, negative charge, because you can clearly see the curly arrow goes to the oxygen. I also got Cl, and I've also got the NH2R group. So the nitrogen positive NH2 and the R group. And what happens is this R NH2 with the lone pair of electrons take a proton, go from there to the nitrogen, and it wants to reform the double bond between carbon and oxygen, and in order to reform the double bond, the C-Cl bond must break, and then all you're left with is CH3 C double bond O, and what you're left with here, NHR, because this has taken a hydrogen, acted as a base, taken a hydrogen. Part D. In practice, ethanol anhydride is used in industrial synthesis rather than ethanol chloride. Give one reason ethanol chloride is not used in industrial synthesis. This is a really nice question because it's that one where advantages of ethanol anhydride over ethanol chloride. The idea is ethanol chloride is corrosive, dangerous to use, dangerous to use. Part E. In step 3, other aromatic products or forms of paracetamol. Draw the structure of one of these other aromatic products. Step 3. Other aromatic products are formed. other aromatic products can be formed? Well, we could. Well, I guess this NH2, you could also have an NH2, so it'd be like. Sorry for the bad diagram, but you'd also have an NH2 here. So what you do is this hydrogen would go here to form NH2, and then you've also have your OC double bond OCH3. So straight line up, OC double bond OCH3. Oh, just put it here. CH3 double bond O here. Question F. Chemists have recently developed a two-step process to produce paracetamol for phenol. In the first step, phenol is oxidized to hydroquinone. In the second step, hydroquinone reacts with ammonium ethanoate to form paracetamol. Complete the equation for this second step. So, react with ammonium ethanoate. Ammonium, NH4 plus ion, ethanoate. Well, ethanoate, CH3COO. So it's going to be CH3COO, NH4. And then you would also then check, you're also going to form, obviously going to form water. Yeah, you're going to form water, and then you just need to balance it, so it should be two H2Os. Calculate the mass in kilograms. Okay, so now we're left with an actual question. What I mean by actual question is, part A, how well you know your mechanism. Part B, how well you know your equations. Part C, how well you know your mechanisms. Part D, A1 question, pretty much, yeah, on advantage of ethanoic anhydride over ethanol chloride, or one reason ethanol chloride is not used. And then part E, this is like again, how well you know your mechanisms. Part F, how well you know your equations. And part G, an actual mass question. So let's go through this. Calculate the mass in kilograms of hydroquinone needed to produce 250 kg of paracetamol. So this is paracetamol, and I'm given the mass of paracetamol. I'm not given the MR paracetamol. Does it give me anywhere here? No. So first thing I'm gonna have to do is find out the MR paracetamol. MR paracetamol. That's gonna be a bit annoying. So you'd go, okay, OH, you've got your C6H6, HN, your C, oxygen, your CH3, and you should get 151.0. That's it, MR. Now I need to find out the moles of paracetamol. Well, the moles of paracetamol is going to be its mass over MR. Cetamol. It's going to be the mass. However, the mass is in kilograms in this case, so I need to convert it into grams. So it's going to be 250. Actually, no, I don't, because no, I do. Because moles, when we calculate moles, mass is in grams always. 250,000 divided by the MR. Now that's the moles of paracetamol. I want to calculate the mass of hydroquinone. So I can clearly see it's a 1-to-1 molar ratio. So the moles of hydroquinone is this, whatever this is, the moles of paracetamol. And therefore, to find out, I'm just going to write it again. Therefore, to find out the mass of hydroquinone needed to produce this much, moles is mass over mR. Therefore, mass is going to be the moles, which I've worked out. So I'm just going to put arrow there, times by the mR of hydroquinone, 1110.0. Put that in a calculator, boom. But, that will give you, so 250,000 divided by 151.0 times by 1110. That will give you 182,000 what? Grams, because mass is always measured in grams and moles in mass per mR. Therefore, we want in kg, 182 kg. So it's not a necessarily hard question, it's just multiple steps. Understanding you have to convert kilograms to grams and then back from grams to kilograms, which shouldn't be a difficult conversion. Question 2, the reaction between propanol chloride and benzene is an example of acylation. Which is the correct representation of part of the mechanism of this reaction? So a correct one. No, it's going from chlorine to the middle of this. No. B, it does look correct, but if you remember, it's actually like this. AlCl, Cl, Cl. You've got your hydrogen here and then chlorine here, and it goes from here to there, not from the Al, from the middle of the AlH bond. So it's actually not B. C, yes, goes from the ring of delocalized electron to the carbon positively charged, the carbon cation. Perfect. And D, therefore, is incorrect as well. Answers to C. Question 3. Data about the hydrogenation of cyclohexene of benzene are given. Delta H is negative in both cases. About the entropy of hydrogenation. Explain the bonding in and the shape of a benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexa 135 triene molecules. The data in your answer. This type of question, I would, especially for this topic, just memorize it, because the mark scheme has got pretty much everything they want you to do, and this question is more than likely to pop up again, because for benzene they can't really ask you that many questions, and more often than not they ask you to compare it with cyclohexa 135 triene. So stage 1, 6 markers. Stage 1, I'm going to talk about the bonding. Now each carbon has 3 covalent bonds. There's spare electrons in a p orbital which overlap to form a pi cloud. Should be the pi symbol, but I don't know how to do that on my keyboard. And it's also got delocalization. Stage 2, the shape. It's a planar shape, hexagon / 6 carbon ring with 120-degree bond angle. Also, I know the carbon-carbon bonds are equal in length. Okay, that's all, your knowledge. Your knowledge of bonding and your knowledge of the shape of a benzene molecule. Now, stage 3, the stability. Now, this is where you're going to probably a lot more students struggle with, because you need to understand what the question is asking you and then apply it to the question. Stage 3, stability. So, well, if I look at this, we've got 1H2, 3H2 here. The expected enthalpy of hydrogenation of cyclohexa 135 triene would be minus 120 times by 3, right? Which is minus 360. However, it's not. It's minus 208. And therefore, the enthalpy of hydrogenation of benzene is 152 kilojoules per mole to power minus 1 less exothermic. So, I would say Get rid of that. Expected. Why does it keep... Okay, something's going on now. I'll just do it here, I guess. Expected enthalpy of hydrogenation of cyclohexatriene, let's just say that, is going to be minus 360 kilojoules per mole to power minus 1. It's just going to be minus 120 times by 3, H2O to 3H2O, kilojoules per mole to power minus 1. However, enthalpy of hydrogenation of benzene is less exothermic. By how much? Minus 208 to minus 360 is less exothermic by 152 kilojoules per mole power minus 1. Benzene is lower in energy than cyclohexatriene, as benzene is more stable. And then part B, the enthalpy of hydrogenation of cyclohexa 1,3-diene is not exactly double that of cyclohexene. Suggest a value for the enthalpy of hydrogenation of cyclohexa 1,3-diene and justify your value. Okay. So the value really should just be between minus 121 and minus 239. That should be fine. So say minus 121. Why? And justify my value? Well, because the double bonds are separated by one single bond / alternating structure, which allows some delocalization / overlap of p orbitals. Question 4, which statement is correct? Nitration of benzene using nitrating mixture of concentrated nitric acid and concentrated sulfuric acid. The answer is obviously going to be HNO3 acts as a base. Question about nitrobenzene. Nitrobenzene reacts when heated with a mixture of concentrated nitric acid and concentrated sulfuric acid to form a mixture of 3 isomeric dinitrobenzene. Write an equation for the reaction of concentrated nitric acid with concentrated sulfuric acid to form the species that reacts with nitrobenzene. So I've got HNO3 plus H2SO4 are forming NO2 plus H3O plus 2HSO4 minus, and we also need a 2 here. And let me just get my textbook for a moment. I'm pretty sure this equation you do need to memorize anyway. I mean, it's on the textbook, I'm pretty sure, so I'll have a look. Yeah, H2SO4 plus HNO3 plus H2SO4 H2SO4 NO2 plus HSO3 minus plus 2HSO4 minus. Yeah, just remember this one. And name and outline the mechanism for reaction of the species with nitrobenzene to form 1,3-dinitrobenzene. It's going to be nitrobenzene, electrophilic substitution. Electrophilic substitution mechanism. Well, I've got nitrobenzene of this species with the NO2 plus reacts with nitrobenzene. Okay, so yeah, it's gonna be like got my NO2 group, O2N, and NO2 plus. Now this bit is key. The nitrogen is positively charged. It goes from the ring of delocalized electrons to the nitrogen, like very close to it. And then what happens is you've got your O2N, that stays the same. And you've also got your partial horseshoe ring, your positive charge, and you've got your NO2 and a hydrogen now. NO2, and you've also got your hydrogen and the middle, this H2 there. Not to the positive charge, just there. Just how well you know your mechanisms. Part C, dinitrobenzene shown were investigated by thin layer chromatography (TLC). In experiment carried out in a fume cupboard, a concentrated solution of pure 1,4-dinitrobenzene is spotted on a TLC plate coated with solid that contains polar bonds. Hexane was used as a solvent in a beaker with the lid. The start line drawn in pencil, final position shown in the chromatogram in the diagram below. Use a chromatogram and diagram above to choose the RF value. So you'd obviously use your ruler, and you should get A, 0. No, not A. You should get D, 0.62 as your final answer. Part D. State in general terms what determines the distance travelled by a spot in TLC. Balance between solubility in moving phase and retention by stationary phase. Give one of the practical requirements when placing the plate in the beaker. Solvent depth. Solvent depth must be below start line. Solvent depth must be below start line. Deduce the relative polarities of 1,2-dinitrobenzene and 1,4-dinitrobenzene and explain why 1,4-dinitrobenzene is greater RF value. So the relative polarities, well, the idea 1,2 is more polar. 1,2 is more polar. 1,2-dinitrobenzene is more polar. And why 1,4-dinitrobenzene has a greater RF value, okay, less polar. Because it is less polar as less attracted. Obviously, you shouldn't say it is, you should say 1,4-dinitrobenzene. Because what am I talking about when I say it is? It could be anything. 1,4-dinitrobenzene is less attracted to polar plate / stationary phase. There we go. Less attracted to polar plate / stationary phase, or you can say slash solid. And part G. Is the student correct? A third TLC thin layer chromatography experiment was carried out using 1,2-dinitrobenzene and an identical plate to that in part C was used in the same conditions, but the solvent used contained a mixture of hexane and ethyl ethanoate. A student stated that the R value of 1,2-dinitrobenzene in his third experiment would be greater than that of 1,2-dinitrobenzene in experiment part F. Is the student correct? And it is 2 marks. So yes, the student is correct. Why? Well, ethanoate is more polar. Well, ethanoate is more polar, and polar isomer is more attracted. Polar isomer is more attracted / stronger affinity to the solvent than before. Question 6. Use your understanding of the bonding in benzene to identify the compound that has the most exothermic enthalpy of hydrogenation. Now with benzene, multiple choice questions on benzene, I can only see a couple of them asking you about, obviously this type of question, and also just calculating, like doing subtractions between cyclohexyl 1,3,5-triene and benzene as well. But yeah, for this one, well, if you look at all of these A, B, C, and D, these are opposite each other. It's going to have the most exothermic enthalpy of hydrogenation. The p orbitals overlap. It's gonna be A, yeah. Okay, question 7. Yeah, like this is not really relevant for this question. Like you don't really need to read that. Possible synthesis shown in the following figure. And I've seen questions where it's like name step 1, name the condition using step 1, name the region using step 2, for example. All 1 markers, and once they add up, that's 5 marks. Hence, you need to know your regions, your conditions, all of them. But it says name and draw mechanism for the reaction step 1. So I'm going from reaction step 1. I'm going from what's going on? NH2 to that COCH3. It's clearly going to be nucleophilic addition elimination. Nucleophilic, and you'll only be able to spot it out quickly. Yeah, super region is ethanol chloride. So yeah, it clearly is nucleophilic addition elimination with acyl chlorides reacting with that. So name and draw a mechanism for reaction step 1. A mechanism. Okay, so I've got this, which I want to do it as a normal format. So C6H5NH2. Nitrogen has the lone pair of electrons, and then I've got my CH3, C double bond O, Cl. So where does this lone pair of electrons go? To carbon there, and then I'll just do it here, I guess. CH3, C, oxygen, lone pair of electrons, negative, Cl. I've also got my NH2 plus. So my NH, nitrogen positive, and I've also got my C6H5. And then another RNH2 with a lone pair of electrons. In this case, takes a proton, acts as base, takes a proton, and it leaves this NH bond. And also, carbon oxygen wants to reform the double bond, so lone pair of electrons to the middle here. In order to reform the double bond, CCl bond must break. And then I've got my CH3, C double bond O, just Cl's left, and I've got my C6H5NH. So I just say NH and then C6H5. If I scroll up a couple of questions, but we've gone through literally this exact same mechanism. I think it was question 1 or something. No, was it? Yeah. Here. Literally the nucleophilic addition elimination. Same steps, and how many marks is that out of part C? 2 marks, and in this case, literally the exact same. Just with different regions, different conditions. 5 marks for part A. But obviously this wants you to go through a lot of it. I think it was 2 marks. It probably wasn't, I'm not sure. 5 marks, so all you have to do is memorize the mechanism, where the curly arrow goes, etc. etc. Part B, a lot of that paragraph of information. It says give reasons for each of the following practical methods. The minimum quantity of hot water was used. Crude product was dissolved and the minimum quantity of hot water was used to ensure crystals would form on cooling. To ensure crystals would form on cooling. The flask was cooled to room temperature before the crystals were filtered off. Solubility is higher if warm. Crystals were compressed in the funnel. Air passes through the sample, not just around it. Air passes through the sample, not just around it. A little cold water was poured through the crystals to wash away soluble impurities. To wash away soluble impurities. How well you know your practicals. Yeah, recrystallization is practical. And it says, suggests the most likely impurity to cause this low value. Melting point of the sample found to be slightly lower than datable value, and an improvement to method, so a more accurate value would be obtained. 2 marks. Most likely impurity, water. And to improvement to the method, well, we compress the sample. Press the sample of crystals. The sample of press the sample of crystals between filter papers. Between filter papers. Press the sample of crystals between filter papers, or you could say give sample time to dry in air. And then question D, percentage yield question. Hopefully, it probably is going to be really hard, but let's have a look. Okay, so it says, figure above is repeated here to help you answer the following questions. It says, an experiment started with this much of phenyl amine, this much of purified product obtained in step 1. Calculate percentage yield in this reaction. So it's obviously not going to be 4.82 divided by 5.05 for 3 marks. So percentage yield, what's the formula? Actual yield That's the first thing I would jot down, because if I forgot the formula, then I can't really get the final mark. Because the first two marks are, I'm assuming, going to be me working out moles, MR, etc., times by 100. So I know the actual yield is 4.82 grams of purified product. So there we go. I need to find the theoretical yield, therefore I can find out the percentage yield, which is actual yield over theoretical yield times by 100. How do I find the theoretical yield? What I can do is I'm given this much of phenylamine in an experiment starting with this much of phenylamine. Now I need to find out the MR of phenylamine. So let's do that. Well, it's going to be C6H5NH2, and I'm pretty sure I know all of them, all the MR of all these values. So let me get my calculator out. So it's just going to be, right, C6H5NH2. So it's going to be 12 times by 6, 72, plus 5, plus nitrogen, which is 14, plus 2, 93. Is it 93? MR of the product. Wait. This much of the product step pertains to step 1. Oh, so I need to phenylamine. So I need to find out the MR obtained in step 1. So what I need to do is find out the MR of the product. So 72 plus C6H5 plus 5 plus 14 plus 1 plus 12 plus 16 plus 12 plus 3, 135. Reason being is because I've got the mass of the purified product. I've got the MR. Now I can find out the expected mass, the theoretical yield. That's what I'm trying to find ultimately. I've got the actual yield. I need to find out theoretical yield. So what I need to do first is I need to find out the expected mass. That's what I have to do. So it's going to be 5.05 times by, well, I know my MR is 135, divided by the MR of this, 93. 7.33 grams, and therefore the percentage yield is going to be 4.82 divided by 7.33 times by 100, which is 65.8%. Part E, write the equation for the reaction as intermediate in step 2. A mixture of concentrated nitric acid and concentrated sulfuric acid reacts to form a reactive intermediate. C6H5, so this plus NO2 plus, so NH COCH3 plus NO2 plus to form C6H4 should carry on NHCOCH3 NO2 plus H plus. You can also do it in like this kind of format, but yeah, you can do it either way. That's why they give us quite a bit of space. Name a mechanism for the reaction in step 2. Again, a classic question. In step 2, that is electrophilic substitution, because we're going from this stays the same. All we've done is added the NO2 group. So yeah, electrophilic substitution. electrophilic substitution, and you can see how many 1 markers F, G, and H just about mechanism. And in part G, sorry, suggests the type of reaction occurring in step 3. In step 3, I'm going from this NO2 to NH2 NO2. What it is hydrolysis. Hydrolysis, and the reagents used in step 4, NO2 to NH2. So I'm using that, or I can say HCl. And that is the end of the aromatic chemistry question paper.